I will have the last 2 pages for this tutorial 1. Here. Encoders. I should bring one, actually. I didn't. Let's go to the web page and take a look. So these are the encoders. Depends on different manufacturer. I think there are different steps for every encoder. So every step is going to send a signal to your microcontroller, so it knows it's actually snap to that specific step. It's not a continuous switch. It's a discrete switch. Has maybe, I don't know, 180 or something steps for the entire 360-degree. So you can use an encoder to send the specific signals to a microcontroller to give a commands to a stepper motor or to somewhere else. If you are using a potentiometer, it's a continuous resistance sensor. It won't be able to give you an accurate position every time. So that's why the encoder is pretty useful. We are going to have a tutorial in this class. We use encoders pretty intensively, I think. So all the tutorials all the pictures comes from one website. And I think you can look at that website, and I have some modifications with the sketch. So you can look at the sketch I have provided on the website for your experiment. But anyway, we are not going to do this anytime soon. Probably it's going to be the very last 4 weeks of this semester. So let's just look at the tutorial first and see what's going on for this encoder component we're going to use. Just how that works. Okay. So for example, the plate here, and you have 2 sensors, and there, imagine that there will be 2 receivers behind it as well. And these bars or the plates are embedded inside the encoder. If you rotate the encoder, it's going to block the emitter's light. If this is the optical encoder. So for example, there is so here is a little emitter, light emitter, and on the back, which you couldn't see right now, it's going to be a receiver. If you rotate it, and this block will be inserted into the middle of the receiver and transmitter, and will block the light. So it's not receiving anything. Okay. So in that case, you can tell actually from the digital circuit which direction this encoder is rotating, and also how many steps this has been rotated. So the way to do that is, for example, every time this is being blocked, you are getting a rising edge for the output. So if you rotate this encoder clockwise, think about it. If you rotate this clockwise, and it's going to snap to a position that the entire block here will be totally underneath the 2 emitters. But it's gonna still travel through one of the, for example, the A emitter, whenever it's traveling to the top of this block. Do you know what I mean? So when you are rotating that, we are rotating this. I'm going to have a little node at the top. I'm going to rotate this. If you rotate it, there are 2 sensors. It is made by only be able to snap to here. It's not able to do like A is on top of this, but this is outside of the block. You know what I mean? However, it is still able to travel. It's going to experience that state, which is A is on the top, but B is not. However, it won't stay on this state. It's going to like this, right? Now it's going to snap to here. For both of these two sensors on top. But during the transition, when A is being blocked by this thing, okay, it's getting a rising edge. But however, at that moment, B is not reaching the top of this block yet. So B is still low, right? So you can tell when A is high, it's going high, B is still low. So this is one state. However, if it is rotating counterclockwise, it's going to be a different story. So when you are rotating this clockwise, you are rotating this one. So A will be on top of this one first. So take this block. You got a rising edge. You can use your Arduino sketch to test, to check. When A is having a rising edge, B should be different compared to the B should be the same as the previous A state because they were here. That's confusing. Super confusing, right? If you look at the code, it makes sense. So now you can check, for example, before I rotate the encoder, I have A and B here, and they have the same state. And the signal is not being blocked. That's understandable, right? Is it? If you rotate it, here will be blocked. So the state of A will be changed. So when the state of A is changed, I can check the previous state of A, if A and B have the same state. If they have the same state when A is changing the state, then I can tell it is rotating clockwise. Because if this is rotating counterclockwise, what happens? Counterclockwise. In that direction. So these two guys are not rotating. Only this is rotating. Like this. So if the entire thing here, if the motor is rotating in that direction, which is counterclockwise, then B will get into here first. Is A changing the state during that transition? No, A is still here in this area. Well, these two, they can only snap to here. So when you are rotating that, these two guys will be on the top at the same time. And if you rotate one more time, A will change the state. A is going to move outside of this spot. Okay. So when A is changing state, do they have the same state or different state before A changes the state? So when A and B are here, right? For example, A and B are here. And now B is here, A is here. A hasn't changed the state yet. So A will change. So before A change, B and A has a different state. So I can check whenever A changes, if A and B have different states, then it's rotating counterclockwise. Otherwise, it's clockwise. Yeah, if you look at this one for a little bit more time, you understand how this works. And this is the code to make it work. Yeah, just probably just read it for a few minutes and see if you can understand this. So I will rate A, state of A, the physical rate function, and see if A is a final result. Doesn't matter how low. And I'm always giving the last state of A. I'm giving it back in the end of every loop. So I can store the last state of A every time. Check. And if A changes the state, because I'm comparing the current state with the last state. If A changes the state, depends on what I just mentioned over here. If A changes the state, I'm going to check if the previous state of A and the current state of B, is they are the same or not. If they are the same, which means it is rotating clockwise. Not, it's rotating counterclockwise. And also definitely, every time it rotates, you detect that rotation, you just count by one. Add a one for counter. It means it rotates for one step, and also counterclockwise or clockwise. If it's counterclockwise at +1, if it's counterclockwise at -1. So you can digitize the entire 360 degrees. It's not hard to understand. Based on what you have done, it's easy for you guys. Don't worry about this if it's confusing you right now. Look at the code, and when you are playing around with the encoder and the stepper motor, you'll get there. Simple. And there's another different type of encoder. It's giving you a different battery output every time. So it's the same thing when you are rotating. It's moving all these bars in the middle of in between the transmitter and receiver of all these sensor nodes. So it's giving you a different pattern of battery numbers, 4 bits. So just getting more different output patterns instead of on and off, right? It's giving like this, right? A, B, C, D. This is a 1111. This is a 1110. This is a 1101, something like that. So you are getting more code. If it's an encoder, then that makes sense, since whenever you rotate it, you can generate a different code. So encoders can be pretty useful. All right, so that's the end of tutorial 1. Let's get into the second one. Yeah, if you like read it, since I have uploaded everything to the website, you can download the Z folder and to find out all these lecture slides. And here's a photo cell resistor we covered in the previous lecture. So when it receives the light, it's going to reduce the resistance internally. That's how that works. If there's no light, then the resistance between these two terminals will be super high. So assume that you know this is a switch, the transistor, it's a BJT transistor. We didn't cover that, haven't covered that yet. It's going to be covered, should be covered in analog. It performs pretty similar to the CMOS transistors. You give a voltage, it's actually a current controlled current source. So if you inject the current to the base, it's going to conduct the top to the column, which is the collector and emitter. So anyway, so if you have, you can imagine if you have a high voltage here, it's going to turn on this channel. Okay. So think about that. Is this a darkness sensor or light sensor? So for example, if this is placed in the dark, the resistance here will be high or low? High. If the resistance here is super high, like mega ohms, what's happening for this pin? So you just think about the extreme case. Super high and something like a disconnect circuit. This is, oh, the, right here. So if this is in dark, the resistance is high, then you can treat this guy as a disconnect circuit. What's the voltage here? Will be ground, close to ground. Why? The reason is it's being shorted to the ground because the any resistor here compared to this huge mega ohm resistor is low, which means it's shorting this pin to the ground. So this is pretty low, close to ground, and this is off. So the transistor, the channel here is open, is off. And what's going to happen? So no current flows through the channel, right? No current flows through this channel. No current means no current. Is that right? No current Yeah, so this is actually a light sensor. Because no current, the relay will not be turned on, and the switch here will be open. So there's no current run through the load. If this is low, resistance is low, which means you have a strong light shines to the sensor. So it becomes like a wire, and it's going to short this pin to the VCC. So it's like a pull-up wire. It's going to pull this pin, pull this port up to VCC. So this channel will be on, and current flows through this relay, and the switch will be closed. So it's a light sensor. Whenever light shines to the sensor, it turns on the switch. There's something I want to skip. But this one is different. Photodiode. Here's the photodiode. If you reverse connect the photodiode in a circuit, it's going to respond to the light intensity not linearly but close. So this is how you sense the light, use your camera. I haven't heard that, right? Since you have been using your smartphone to take pictures all the time. So all the sensors in your smartphone, they are photodiodes. So they fabricate all the photodiodes on the CMOS, the silicon die, in an array, pretty much like millions of pixels. Every pixel has an active photodiode in there. Okay, and they are being reverse biased for every single photodiode. When the photodiode is being reverse biased, it's going to respond to light intensity linearly. Is that interesting? So when you reverse bias the diode, it's not conducting, right, at the very beginning, since it's reversely biased, because high is on the cathode, low is on the anode. But however, based on that, if you shine light to the photodiode, there will be a photocurrent flow through the diode in this way, from top to bottom. It's based on the physics. Okay, so if you reverse bias it, then shine light to the photodiode, there will be a photocurrent being generated internally inside the pin junction. So that's how you sense the light by the camera, CMOS cameras. And that current will flow through where? So if you ground here, and the current is going to flow from top to bottom, definitely will flow from the output across the resistor to the ground. So what's going to happen? So that's a filter. That's a low-pass filter. Don't worry about that one for now. But if this one, you can just imagine this guy is a current source. It's going to draw current in the circuit, can force the circuit to flow that amount of current in the circuit. So what's happening? If there's no light, then no photocurrent. If you shine light to the photodiode, it's going to generate photocurrent. Flow from where to where? Do you have any other paths in the circuit? No. So it has to from here to here, right? From here, an output here to here, and then to the ground. All right. So in that case, current flow through a resistor will generate a voltage drop. All right. So it depends on the current intensity, you are getting a different voltage, which can be used for imaging. So you are actually using that analog voltage to tell the intensity of the photon or the light. That's how every single CMOS imager works in your camera, in your smartphone. And this amplifier with a resistor on the top, it has a similar structure compared to the inverting amplifier, but it's also called TIA, transimpedance amplifier. The reason is it's converting current into voltage. That's why it's called transimpedance amplifier. Impedance is 1 over resistance. The reason is the gain here is R, because input is current, output is voltage. V over R, V over I is R. It's exactly the resistor here. So if somebody asks you what's the gain for the transimpedance amplifier, it's going to be exactly the same value as the resistor here. So it can be really high. If you have a 1K resistor, it's going to be a 1K gain because converting current to voltage. Skip these ones. LiDAR, important. So it shoots light or laser to an object and detect the light bounced back from the object. And the speed of the light, is c, right? 3 times 10 to the 8th meters per second, if I'm right. And because you have a pretty fast electronics, so you can actually get a time between the LiDAR shoots the laser and it receives the laser. So it is able to calculate the duration between these two time points. And since it's a round trip, so you just need to use the speed of the light times the time and divide by 2, so you can get the distance per trip. Okay, that's the distance between one thing to the other object. So the cops use this one to detect your speed on the highway. LiDAR. There's another application. If you have a LiDAR which can scan in a room, if you can do this quickly, you can even have a 2D image for whatever you have in the room. Since you are doing this quickly, right? Imagine here, I have a LiDAR here, a LiDAR laser, and there are so many objects in the room. If I scan this, I can literally get a pixel for at this line. I don't know how many points, but for example, 100 points. So I can probably plot that table and that printer. So I know there's something in this line, and I move to another spot, and I can do the same thing. So in that case, I can do a 2D mapping, or even 3D if you can scan in this direction as well. That's another application for LiDAR. The auto driving, what do you call that? Autonomous driving car. So the auto driving car use LiDAR to detect any object around that car. I believe Tesla's model, I don't know which one, but they have to use this technology to detect whatever is around that car, because it is able to run quickly because the laser is fast. If you use ultrasonic, probably you won't be able to do this, get that feedback really quickly. So laser is probably the only option you can do. It's scanning really quickly, it's rotating. So actually you are getting a 2D map or even 3D map in real time. So the robot on the left side is a spot from Boston Dynamics. And there's a LiDAR sensor being mounted on the top. And also, like we mentioned, it's being used for detecting speeding on the highway. Here's another laser. I don't know if this is LiDAR exactly, but it's super useful. The reason I know this type of sensor is I used one of them when I was in my graduate school. If you buy it brand new, it can be super expensive, over a couple $1,000s. If you buy it on eBay, I'm pretty sure you can find a functioning one, and with a reasonable cost, because they directly disassemble this from the assembly line in the industry, in the factory. The factories probably they will have multiple of these sensors mounted to their assembly line, and whenever they're updating their system, probably they're management team will post all these unused ones to eBay and try to sell it in a pretty low cost. And they are super accurate. So this is a distance or displacement sensor. So it shoots a laser beam to an object and get feedback. And it is able to do this quickly. So whenever that object is moving or not in the desired spot, it is able to detect that variation. And the sensitivity is super high, like in the tens of nanometer level. So if you are trying to detect the displacement in that level, you definitely do not want to use the, what's the name of that sensor we mentioned? LVDT, right? Remember? The linear, yeah, ultrasonic is even more rough. I mean, LVDT is a little bit better than ultrasonic. So LVDT is a linear variable distance. I forgot what is T. LVDT and L, there are two, right? So transformer. T means transformer. So these two distance sensors, they are on the slides. You can find out. So the sensitivity is not in the same level. Highly recommend this one. It's not expensive at all. So the disadvantage of this one is it's probably not, you couldn't use it for water, liquid. So if you are detecting displacement of the liquid surface, maybe you are not getting accurate feedback. That's something I know. That's the one I bought a couple years ago, actually 5 years ago. I really enjoy it actually. So you have to part it up in this range, and you have a ground pin and analog output in this level. But however, it ranges from -4 to 4 VDC, but it can change the offside to lift the signal to a 0 to something. So you can use your ADC to capture all these analog outputs. Something like that. So let you know if you are detecting a distance or something for the robot or for anything else with your microcontroller applications, consider this one. Super accurate and not cheap, not expensive at all. PMT, which is we have a couple of PMTs in the lab. It has all these. It's an optical. It's a photon detector, and very sensitive. So it has a input. So when lights arrive, this port will get inside the PMT. So PMT stands for photomultiplier tube. And it's going to hit this type of material called diodes, which will be able to emit electrons whenever a photon hit it. So it's going to convert photon into electrons. And if you have different stages of voltages, you can amplify that electron emission exponentially for every stage. So one single photon get into here will be amplified and amplified into a lot of electron emission and finally arrive here. So the output signal for this type of sensor will be current. It's going to be electrical current. And you have to have a transimpedance amplifier or TIA. Keep in mind, if you see TIA, what does TIA mean? Transimpedance amplifier. You have to use a transimpedance amplifier to convert the current into electrical or analog voltages. So here's a transimpedance amplifier. You might be thinking this is an inverting amplifier, right? Very simple inverting amplifier, because the signal goes into the inverting terminal, and I got an input resistor and feedback resistor. If we are not looking at this cap, it's nothing but a low pass filter, and we only look at the gain for this guy is going to be this over this and minus, right? So this minus this over this will be the voltage gain. If you are looking at the voltage, in terms of voltage, it is an inverting amplifier. But however, it has another name. If the input is a current signal, then this one becomes a TIA. Keep in mind, All right, so current goes in here and will flow in this way. Why? Because this guy has a super high input impedance. So nothing can get inside the amplifier. So it's flowing like this. And arrive the voltage, output pin. And since current flows through these two resistors, and it's going to generate a voltage gain. So times the resistor will be the voltage output. All right. And then here is the voltage follower. So finally it converts current into voltage and arrives the output. So I know this can be a little bit confusing if you probably already forgot everything for amplifiers. So I have a pretty brief or simple homework assignment to get this reinforced. To derive the voltage gain, differential gain, common mode gain for instrumentation amplifiers and difference amplifier. And I have these lecture videos posted in the past semesters, so you can go back to. I have the link posted on my website, just underneath the homework assignment. Just directly go there and check out if you forgot. Do that again here, so it'll be helpful. And these are the two image sensors probably exist on the market. So the first one is called CCD. So CCD means the charge coupled device. So that's a package to hold that CCD chip in the middle. And here's the cross-sectional view of the CCD. So it works like this. It's going to convert photons into these charges, for example, electrons, in the substrate. And you are going to, so the electronics is going to activate every single electrode on the top of that part, the well, sequentially. So it is able to move this chunk of charges to the next one, and then the next one. It's like the charges being accumulated underneath the specific electrode first, and then you activate it one by one to move it out from the array. Because this is just three of the pixels, but you can imagine there might be millions of pixels. It's in a 2D array. And you have to move every single signal underneath the electrode one by one, so you know which pixel should be which intensity. Then you can reconstruct the image afterwards. That's how the CCD works. So here's a CCD diagram. So you have, for example, you have all these different wires, like 4 wires are controlling these electrodes, and it's going to move the charges in that direction sequentially by giving some signal like this. So activate every single electrode one by one. And that's a readout circuit for the charges. So the charges is being converted into voltages. So the current flows through here, and create a voltage drop across this resistor. So you get a voltage signal over here. And the voltage signal will be amplified by this guy and eventually converted, be received by the ADC. I see the difference between CCD and CMOS. Okay, so here's the CCD. They both have all these pixel array, like taking the image. And for example, the signal here, the charges being stored underneath this electrode will be moved downward to the bottom line, to the bottom column, and will be shifted to the right, one by one, because you have a pretty fast digital system. So when you are pumping out every signal point, you can still rearrange them somewhere and to form that entire picture later. That's how the CCD works, because it has to move every single, the charges stored underneath every single electrode to the bottom and then shift it out. So which means it's going to be slower compared to the CCD array. So the way the CCD array works is it also has, for example, you can design one row of ADC at the bottom, and you have a column decoder and a row decoder, two decoders here and here. Yeah, we are going to learn about decoders in spring. All right, decoders. So you can address. It's like X and Y coordinator. So you activate, for example, this column and this row, right? So the charges being stored in this pixel will be selected and be sent to here to amplify. So you can do this. You can get a signal from one row at the same time, because for this decoder, you can pick up this entire row, and everything will be sent to here at the same time, and then being converted to digital signal. So you can do it row by row. And some extreme cases I've seen a couple of years ago, and I think that's a professor in UC Irvine. He developed a super fast CMOS imager. So it has one ADC for every single pixel. So which means you have to have a lot of circuits beside every single pixel. So there's a term or parameter called aspect ratio will be lower. Since you can imagine, if you have the entire footprint here being occupied by one photodiode, which is one pixel, then you are getting a bigger image. If you only have, for example, this is one pixel, but only very small part of it is for photo sensing, but all the rest of them are, ADCs or something else, the aspect ratio will be lower. You are probably losing information. That's a readout circuit for CMOS. We can skip that one. Okay, so the ultrasonic sensor, and we have a homework assignments regarding this. So the way that works is, so for these two ones, it has a ultrasound emitter and a receiver. Okay, one emitter, one receiver. I don't know which is which, but one is emitter, one is receiver. And so the emitter emits the ultrasonic signal and will hit the object and being bounced back. So the echo will be received by the receiver, and because you know the speed of the sound, so you can calculate the distance from the sensor to the object. That's how that works. But however, when you are working with Arduino tutorial on the website, probably you have done that. It's totally controlled by a library. You actually don't know what's going on. But we're going to have a homework assignments to let you program the protocol here. So here's how that works. If you read the 4 pins, what are they? Can you let me know? What are these pins? Can you read it? VCC, trigger, echo, and ground. So VCC and ground, just power and ground. And there's the trigger, there's the echo. So all these 4 pins will be connected to where? The pins. That's a sensor, right? They will connect the pins to the microcontroller. Is this course that boring? All right. You need a microcontroller to interface with this sensor, right? So VCC and ground connect to the 5 volts of the Arduino board. And trigger and echo should be the digital pin. One is input, one is output. Which one is input, which one is output? Because you need to send a signal to the digital pin so you can trigger this. Right? Because whenever you have this signal up and down, something like this, it's going to send this ultrasonic signal from the emitter. So these are voltage signals. This is not. This is a sound signal. This is drawn in this way, but actually this is not voltage. They are sound signals, ultrasonic signals. Okay. So you send, or the microcontroller is going to send this trigger input. So if you are programming this by yourself, what do you need to do? In a loop. Then pull it low. Okay, so you can create a pulse, a single pulse. If you keep this on keep this high, then probably this will not be created. Keep in mind. So that's the trigger signal. Pull it up, stay for tens of microseconds, and pull it down to ground. Then after this module receives that pulse, it's going to create that ultrasonic signal from the emitter. So it's going to send out this ultrasonic signal to the object. And whatever is being, so after a certain specific duration, this will receive a sound signal, right? And what's going to happen? So the echo, so it's going to receive it and being processed by the circuits on the module and provide a pulse like this at the pin of echo. So after you send this signal, you start a timer. And after you receive this echo, you stop the timer. So you can get the duration between here. All right. So that's going to be the time for one trip or two trips. Two trips. Right? Two trips. 1, 2. And you need to divide that number by 2 to get the distance between the sensor and the object. So here is the original code from the library or from the kit, the company who made that kit, Algo, Arduino, right? You can definitely use this. So there are these two pins, and you can definitely use the library, I think, here, SO4 or something, rate, distance. But also you can use this one as well. So here's the code. You can replace this one with this one. So if you don't have a library like that, you can still program the protocol to make it work. So this is one of the homework assignments. I think we have 4, probably. It's on the website. Just check it out. Another thing you need to know, piezoelectric. How many of you have heard about it? You? There? No? You? Okay. So this is a kind of device can convert pressure to voltage and voltage to pressure. It's pretty interesting and very useful as well. I have used this for many years, and so the one I used is voltage to deformation converter. So I apply a voltage, so it's going to deform, and if I turn on the voltage, it's going to come back. So if I apply a series of pulses, it's going to vibrate like this. Okay. If you give a pressure, it's going to create a voltage, so which means you can create a pressure sensor using a piezoelectric device. So if you see the diagram, you give pressure, you can detect the voltage. And somebody have been thinking about, I don't know if this has been realized or not. They are thinking at the traffic light, at the cross street, because the cars will stop in front of the traffic light, right, for waiting for the green light. So they're trying to embed a piezoelectric sensor on the ground. So whenever the car stops on that, give a pressure and can convert that signal as the voltage to power up the lights. There might be some products already on the market, but I don't know if any of them are commercialized or being installed in real life. Maybe. So there are quite a few different types of piezoelectric sensors. I think this is one of them has been pretty popular on the market. So they can use this thing to detect vibration. So look at the code. Let me know how that works. There's even no amplifier, but probably it's already amplified after the module. So it's using an analog rate. So you're expecting the signal is being connected to where? To the ADC, right? So it reads the analog voltage, and whenever that voltage is larger than a specific threshold, you can define in your sketch, and it's going to turn on the light and turn off. So it's going to blink. Another one is super popular as well. A lot of research institutions are making all these devices for research. I don't know if it's being commercialized or not, but a lot of people are saying this is promising and blah blah blah. So you can fabricate a device, a piezoelectric device on the surface of a substrate, and whenever it is conducting a sound vibration, and it's going to create a voltage. So the surface. For example, if Trevor put his hand on the table, if I knock here, he's going to feel that, right? So you can tell the vibration is actually being transferred to that location. The same concept here. If there's some vibration are transmitting on the surface of the table, then the other side can convert that vibration into a voltage. That's for that sensor. I think there are some commercial equipment have been developed, but just not sure if this is being widely deployed in a hospital or anywhere. Not quite sure. For capacitive sensors, sensing capacitance. Again, this is one of the paper I published in my graduate school, and there's a really good capacitive sensor on the market from AD. It's called AD 7745. So if it starts with AD, who makes it? Analog devices, right? And the sensor of this type is called CDC. So CDC means capacitance to digital converter. Just look at the name. So delightful. Why? Yeah, and also the output is digital. Goodness. So capacitance, something in the real world. I don't care. I just need a digital signal. Just tell me the binary numbers so I can use it. You don't need amplifiers. You don't need anything, filters, nothing. You just need to be lazy. That's it. And grab Arduino and find out the library, connect to the SPI or I2C. And let me see, what's this? What's the protocol? So tell me, what's the protocol? Output. Look at the chip. What's the output signal? Come on. Is that I2C? Why? SU and SDA. So capacitance directly to I2C. My goodness. Whenever people have been making all these devices so easy to use, which means it's super hard to make. They have to have super talented engineers in the company to make this happen. That's why they're the top one company to make ADCs in the world. And if you're looking at the sensitivity, oh my goodness, I can tell me my experience since I have been using this for a couple of years in my graduate school. 4 femtofarads sensitivity. What does that mean? I know, but when I was dealing with this sensor, I have a reader, I displaying the capacitance, on the LCD or anywhere. I sit just in front of the sensor. I couldn't brace. If I brace, the capacitance will change. And sometimes if I just walk around or just stand up or something, the capacitance will change a lot. Just because the air from my body, being pushed to the sensor, it is able to sense it. All right. So something I need to know is kind of like a common sense. So you should know that for touch screens, there are two mainstream touch screens. One is capacitive touch screen, another one is a resistive touch screen. Which one is more sensitive? Let me know. Capacitive. And I would like to know one of my experience with a Garmin, how to pronounce it? Garmin. Back in 2012, when you are still in middle school, or you, 2012, high school, probably middle school, I think. Middle school, not high school. High school. Um, I was in my first year of my PhD, and I came to the U.S. and I bought a crap used car, 1998 Camry, and no GPS, so I bought a GPS, $120 from Amazon, Garmin, and I was trying to push it, to type in all these address I need to use, and I found out my skin just couldn't work, and I don't know why because I normally I use my fingers for the smartphone somewhere, so I expect it's gonna work, but actually it's not working, and I have to use a pretty hard thing to push it, or use my nails to point to all these push button on the screen to make it work. And I didn't know why at that time, but later on I know. A couple of months later I know because of what? It's a really old GPS, and it's being made by all these resistive touch screens. So it's not sensing your finger because when you are touching the touch screen of your smartphone, use your finger, use the skin, it's sensing the moisture of your skin and change the capacitance. So it is able to sense that little tiny capacitance change to give a response. But however, for the resistive ones, you have to physically touch it and to short these two wires, this cross section of that pixel, and make the resistive voltage change between these two terminals because it's connecting another two resistors to the network, so it's changing the voltage. And so you can imagine it's not going to sense moisture. It's going to sense a mechanical touch point. You have to use your finger. I don't think any of the resistive touch screens are still popular right now. If you buy a Garmin GPS, probably you are not, but I'm pretty sure they are not going to make any resistive touch screens anymore. All of the screens should be capacitive, so it's not really hard to modify or operate. So here's a touch screen, right? So touch it, it's going to sense the capacitance at this point and give a response. Here's a fascinating invention. So that's the accelerometer and the gyroscope being fabricated in one tiny IC chip. And that's going to be the main sensor you are going to use for a couple projects in not only this class, but also the microcontroller class as well. So it's called MEMS. I don't know if you have heard about MEMS. MEMS, micro electrical mechanical devices, something like that. So MEMS has been a very popular research topic in the past 10 to 20 years. And a lot of products has been converted to commercial products like this one. Can you imagine that your accelerometer, which looks like a IC chip, there are a lot of things going on inside. When you are shaking that sensor, so all these wires are actually moving inside the chip on the silicon die. You are probably thinking, hey, I have seen a silicon wafer. It's like a glass. If you bend it, it's going to break. So why all these wires are made by silicon, they can move around but without being broken. So what's going on is it mounts. So for example, all these joints, So I don't know the material. They can be metal, right? Probably metal being coated by something. But definitely you can tell all the bars here, if they have a specific distance, the capacitance between the bars will vary if the main frame here moves. They can move on the surface of the silicon die. It's like a machine inside the chip. It's moving. If you shake it, it's going to move in a macro level or even nano level on the chip. So when it moves, the capacitance of C1 and C2 are changing. So you can tell, it depends on the capacitance changes. You can tell how much this has been moved. You can calculate the acceleration. But however, I mean, just think about it. Is that magic? You have a very, very tiny, in a nano level, mechanical machine inside the chip. And when you vibrate it, it vibrates inside the chip. And there's nothing attached or nothing bound this frame to the substrate, actually. So there's nothing at the bottom. So it moves, just moves on the surface in a nano level. But it's not being broken. Why is that? If you can see, you can imagine that it's gonna get deformed to some extent, right? But why it's not broken? Here's the structure of the accelerometer in the chip, but it's not broken. It's actually pretty robust. So whenever you fabricate the material into a nano or macro level, the physical structure totally get changed. The rigidity and flexibility and everything, the physics of the material is totally different if you deal with it in the macro nano level. That's amazing. I have made some of the 3D structures of other devices, but I mean, make all these things, it's super complicated. You probably have to spend 24/7, probably not, but 40 plus hours every week in the clean room for your entire PhD, 4 years, 5 years to make something similar. Maybe it takes time. So that's why we have all these accelerometers in our smartphone. Whenever you tilt it, the screen will be tilted, will be adjusted as well, because there's such a sensor, small sensor inside can sense the gravity. Where's the gravity? So can tilt that screen for you. All right, we'll cover the rest of the slides next time.